So this work is about relaxed queues and stacks from read-write operations. I'm Armando Castaneda. This is a joint work with Sergio Rajsbaum and Michel Raynal. So linearizable non-blocking or weight-free implementations require synchronization. Sometimes a lot of synchronization, which might limit scalability. It has been shown strong step complexity lower bounds for some data types. Also, it has been shown that sometimes expensive synchronization mechanisms are unavoidable for some data types, including queues and stacks. So people have proposed relaxed queues and stack implementations. And as far as we know, all these implementations use read-modified write operations. So no one has tackled this problem from the perspective of computability. So the only work that has taken this perspective to some extent is the one by Shavit and Tobefeld. They study the consensus number of several queues and stack implementations, relaxations, but they don't provide any implementation at all. So it's known that queues and stack have consensus number 2, so there is no read-write, non-blocking, or wave implementation of this data type. So the question we started with in this paper is if there are many meaningful queues and stack relaxations with read-write implementations. So we want to study what can be done using only reads and writes when we study queues and stacks. So we care about reads and writes because these are the simple base operations that any model can have, and they have consensus number 1. So contributions, we propose the notion of queues and stack with multiplicity, and we provide 2 algorithms, a weight-free stack implementation with multiplicity from reads and writes operations, a non-blocking queue implementation with multiplicity from reads and writes operations. Also, we introduce the notion of queues with a weak empty value. We provide a weight-free queue implementation with weak empty from consensus number 2 objects, and then we provide a weight-free queue implementation with a weak empty and multiplicity from only read-write objects. So I will explain the ideas in these contributions, and I want to start talking about correctness conditions. So linearizability is a standard correctness condition. It says that operations can be totally ordered while respecting the execution order of non-concurrent operations. So the idea is that we have an execution, and then for each of the operations, we pick a point inside of the interval of every operation. That's its linearization point. This points induces a sequential execution, and this sequential execution should satisfy the specification of the data type of problem that we're talking about. So linearizability is a generalization of linearizability where concurrent operations now can be linearized at the same point, like in the figure we have here. So now several operations can be linearized at the same point. So we kind of move from dimension 1 in linearizability where everything is on a line, and now we have several lines where several operations can be linearized at the same time. So an interval linearizability is a generalization of set linearizability where now the points can be stretched and now operations can be linearized in an interval. So now we can talk about interval linearizations. So now what we need to find is inside of the interval operation an interval, which can be a point and or an interval, and then we have this interval linearization. Like in here that we have this interval that spans several operations, like these points are an operation, these are an operation, and this spans also this interval of another operation, all the time respecting the order of non-concurrent operations. Interestingly, these 3 correctness conditions induce a strict hierarchy. So we have that linearizability is strictly contained set linearizability, and set linearizability is strictly contained interval linearizability. Here, contained means what you can specify using these formalisms. So progress conditions, we consider 2 standard conditions, non-blocking and with freedom. Non-blocking means that as long as a process takes steps, at least one operation completes. So that means that if some operations might be blocked in execution forever, but if that happens, there are infinitely many operations that are completed. With freedom means that as long as a process takes steps, all its operations complete. So this is the strongest progress condition. So with freedom implies non-blocking, but not vice versa. Non-blocking does not necessarily imply with freedom. So queues and stack with multiplicity. So multiplicity essentially says that concurrent, the queue or pop operations can take the same item. But that can happen only if the operations are concurrent. So we still require the FIFO LIFO order, depending on the case, and we specify this using serializability. So for the case of the queue, we have now this execution. We have here a push operation, then here another push operation, and then we can now have two pop operations that take the latest item, because this is a stack, that they are concurrent, they take the same item. Here we have again this push 3, and then these two concurrent operations, they take the 3. Okay, so for the case of the queue, we have something similar, but in the FIFO order. Here we have an in queue, another in queue, the queue, and in queue, and then we have 3 the queue operations that take the same item. This is the idea of queues and stack with multiplicity. So for the implementations, we adopt a modular approach in both the case of the queues and stacks. So we start with some known algorithm, and then we derive from that algorithm our implementation. For the case of the stack, we start with this nice and simple linearizable weight-free stack implementation from Affect, Gaffney, and Morrison. So it's based on consensus number 2 objects. It has an infinite array of items. These are swap objects initialized to bottom. And then we have a top. This is a fetch and increment object, which points to the top of the stack. So in the items array is where the items will be stored. So whenever a process wants to push an item, it does fetch and increment on the top object. That reserves a slot in the items array, and then it puts the value there. So these two operations are not atomic, so it might happen some time between reserving the slot and then putting that in the slot. So when a process wants to take an item, perform a pop operation, it just reads the top of the stack, and it starts reading from that position to the bottom of the stack, from top to 1. And every time it does this swap operation so that it can get an item. Whenever it gets something distinct from bottom, it gets an item and it returns that value. If it gets nothing, after scanning all these entries, it returns empty. So the algorithm is very simple, but the linearization proof of this implementation is not easy at all. Actually, when one starts playing with the algorithm, with running some executions, it's easy to see that linearizability is not an easy task. So the idea in our implementation is to replace this top object, this fetch and increment object, with a relaxed version of fetch and increment, in which concurrent operations can read the same value. So, and this is the first idea. The second idea is that we will replace every entry of items with a container, with multiplicity. So it's a relaxed version of a container. A container provides 2 operations, get and set. It's like just a set. So it provides 2 operations, get and set. So the set operation puts something in the container, and then the get operation gets something from the container. It doesn't. There is no order that should be required. So this idea of container with multiplicity is that concurrent get operation can obtain the same item. So this is what we do. So first, we need to replace this top fetch and increment object with only reads and writes. So we use any read-write implementation of a counter initialized to 1, and then this is what we use to handle the top of the stack. So now instead of doing fetch and increment, we do these 2 operations, read and increment, which is not atomic. So there might be something happening between these 2 operations. So now it's clear that 2 processes can get the same position in top. So to resolve this issue, we do this thing of relaxed container. So now every entry of the items in the original algorithm is replaced with an array, with an entry dedicated to each of the processes. So now when a process deposits a value in items, now gives 2 entries, the row of the array, which is the container, and then its position, its ID dedicated to the position dedicated to the process. So when the process writes this value, it's logically doing a put into the container, this container at this position. So now this part of the code, which is a for where it scans all the positions in a given container, it's implementing a get operation of the container. So every time a process wants to get a value from the stack, it reads the top and it starts scanning all the containers from the top of the stack to the bottom. So it goes to one of these containers, it starts scanning all the positions in the container and trying to get a value. So that implements the get operation. So before we had this swap operation so that only one process can get one item, but we don't have that anymore. So that swap operation is implemented just with reads and writes in a very simple manner. Every time a process is reading an entry of this container, if it scans all these entries, if it reads something distinct from bottom, it just returns that value. But before, it marks this entry as taken and it writes again bottom. But now the observation is that since this is asynchronous, there might be many things happening in between. It's possible that two processes read the same entry at the same time, and they both see the same item and return the same item. But this can happen only in concurrency, in case of concurrency. And these are the two main observations for proving self-linearizability of our algorithms. So the first one is the one that I just said before. Now push operations can deposit at the same row, that means at the same container, if and only if they are concurrent. This is the first observation. The second observation is that pop operations can take the same item, but that can happen only if and only if they are concurrent. So these are the two observations. So the serializability proof is a reduction proof to the base algorithm. So what we do is that we take an execution of our algorithm, we remove, we take for each of the items, if this is taken by more than one operation, we remove all these operations with one. We just keep one of them. And then that execution is linearized using the linearization proof of the base algorithm. And once we have this linearization, we go back to our implementation and we put back the operations that we removed. And this is how we obtain self-linearizability. Self-linearization. So the approach seems kind of simple, but it's not. There are some subtleties, but we relied on this linearization proof of the original algorithm, which is kind of hard. So for the case of the queue, we do the same. We follow the same approach. We start with this simple linearizable non-blocking queue implementation of, which is a variant of implementation of Lee or Herrlich-Wing. So the idea is pretty much the same in this, like in the case of the stack. So we have this array of sub-objects where the items will be stored, these array items, and we have this tail, which is a fetch and increment object that points to the tail of the queue. So whenever a process wants to do a queue, again, it reads the tail, reserves a slot, and then it puts the item in that slot. And the queue is, it's essentially, it follows the same idea. That the process starts reading from the beginning of the queue, from position 1 in the items array, to the tail. And it starts reading and it tries to get something doing swap operations. This is in line 11. It's trying to get something doing swap operation. If it gets something distinct from bottom, and it's an item, and it returns that item. Otherwise, it reads again the tail to see if to check if there is nothing new has been enqueued in the queue, and if there is nothing new, the line 16 is satisfied, so it can declare that the queue is empty. Otherwise, it restarts. So it's easy to see that this implementation is non-blocking. It's non-blocking. The enqueue operation is wait-free, but the queue operation is non-blocking because of this thing that the queue operation can be scanning again and again if there are new items that are stored in the queue. We follow the same approach to obtain our read-write implementation. Exactly the same idea. The fetch and increment object is replaced with a read-write counter, and the fetch and increment operation is implemented using these two operations. And again, we implement this relaxed container with multiplicity in the same way that we did before. So this is the way we obtain the self-linearizable non-blocking queue with multiplicity. This is non-blocking because our base algorithm is non-blocking. Okay, so before going to the next contributions, I would like to stress, explain 3 implications that we get from our algorithms. These 2 algorithms that we just saw. The first one is that we avoid closely synchronization operations. It has been shown by Ati et al. That any implementation of a stack or a queue must use either read modified write operations or read after write patterns, which is like the one we use in the flag principle. So these 2 synchronization mechanisms are costly, and with using this notion of multiplicity, we can evade these results because our implementations use only reads and writes and do not use these kind of expensive mechanisms, read after write. And the same happens for work stealing. Work stealing is a popular load balancing dynamic load balancing technique, and it has been shown by Ati et al. That any implementation of work stealing must use read modified write operations or read after write patterns. But our algorithms imply work stealing with multiplicity solutions using only reads and writes, so we can evade again these impossibility results for this data type. Third, our implementation implied k out of order queues with multiplicity using only reads and writes. K out of order is a realization of queues in which introduced by Kirsch et al., in which essentially the queue operation can take any of the latest k values in the queue. So this is an implementation, a realization that has been proposed, and Kirsch et al. Have proposed implementation using only using read modified write operations. So using the notion of multiplicity, we can obtain k out of order with multiplicity using only reads and writes. Okay, so now we also introduce this notion of queues with empty values. So we obtain non-blocking implementation of a queue. So a natural question is why not to obtain a weight-free ReadWrite queue with multiplicity? So if we start with the base algorithm, which is linearizable and weight-free and uses consensus number 2 objects, we could derive maybe a weight-free implementation using the same techniques. So this is not so simple because this is an open question. It's an open question. It started in '93, actually, from Afek et al. If there is a linearizable weight-free queue implementation uses consensus number 2 objects, that is unknown, and there is people that have been working on that, but there is no solution to that problem. And the challenge in this for implementing queues using consensus number 2 objects is in detecting if the queue is empty. Sometimes we call this as the chasing the tail problem. As you saw in the base algorithm that we used, it has this condition if it can declare or not that the queue is empty. Actually, it's hard how to declare that the queue is empty in all cases, and being weight-free. So we propose a relaxation of the queues with a weak empty value. So essentially the idea is the following: the queue operation if in an operation the queue operation returns weak empty, then the queue might be empty. From the perspective of that operation, the queue might be empty. It's not necessarily empty, but it could be. So we specify this using interval instability. So in this relaxation, we have something like this. We have enqueues, and the queues returning values or empty values as usual. But we might have now this enqueue operation like the one here, in which this will be linearized not on a single point, but it will be interval linearized. So its linearization will span an interval. And the idea is the following: when the queue operation starts, the queue is in a state. In this case, it has 1 and 2. And then while this operation is running, these 2 items are taken. So from the perspective of this operation, these 2 items are taken, so the queue might be empty. Because it might not be, the operation might not be aware that there is a new item in queue. Like in this case, we have these 3. So we know that there is a new item because we see from the picture, but the operation might not be aware of this item. So it declares, it plays conservative and say, well, the queue might be empty in this case. So this is the idea. And we obtain weight-free implementation using, again, the same base algorithm that we used before. So what we do now is that we take this algorithm, which is non-blocking, and we use this notion of queues with weak empty values to go from non-blocking to weight-free. So we obtain this implementation, again, from consensus number 2. We don't modify that in a very simple way. So the idea is that instead of scanning again and again the tail, we just scan 2 times. And if the condition for returning empty is satisfied, we return empty. Otherwise, we return weak empty. And that's it. That's it. That is the only thing that we do. It's a very simple algorithm. Although the algorithm is very simple, the interval inasability proof of the algorithm is not simple at all. Actually, it's the most complex proof in the paper. And even though that we follow this reduction approach, again, we reduce the interval inasability proof to the inasability proof of the base algorithm, but still the proof is kind of complicated. But this is the way we obtain this weight-free queue using objects from consensus number 2. And then to obtain a read-write queue implementation with multiplicity and with weak empty, we do the same trick by replacing the tail with a relaxed fetch and increment, and replace each entry of item with a container with multiplicity. And this is how we obtain the same. We follow the same approach as before. So to conclude, we have future work. So we want to study multiplicity for other data types. We want to see if our implementations could lead to a scalable read-write implementations of the queues and stack, or any other data type. We have some partial results for work stealing. That's a good candidate. We think that there is something in there, so we'll dig more on that in the future. Also, we want to know if multiplicity leads to scalable implementation regardless of the base operations. In this paper, we focus on reads and writes because we had this perspective of more on decidability, what you can do with these operations. But in general, we are focusing on scalability. It doesn't matter the base operations. We just want to have something which is faster. And that's it. Thanks for watching.